Hello. Okay. Can you hear me?
Yes, sir.
All right. So let me just recall that pair and list thing. I think it is clear to most of you. Can you tell me how many of you have still doubt in this pair and list thing? Anybody has doubt in what is a pair and what is a list? Hello. Okay. All right. So let me test. Can somebody tell me the answer to this? Without trying it in your machine?
It's a pair of two pairs.
Pardon? Pardon?
A pair of two pairs.
This will be a pair of two pairs, but what will those pairs be?
Again a pair.
Yeah. So this will be 1.2 dot 1.2. Yeah. Okay. Now that's a very strange notation, but it just means the same thing, 1.2 dot 1.2. Okay. Now if I change, so what will be cons 1, 2? Cons 1, nil. What will be this?
1.2 1.
1.2 1.
So pair of 1 and 2 first,
Yeah.
and then whole list 1 with 1.
Yeah, so it will be a list which contains pair 1, 2 and 1.
Yeah.
Okay. It will be a list which contains pair 1, 2 and then 1. And finally, what will be? Cons 1 nil and cons 1 nil. What will be this?
So first is 1 pair, then 1.
What is one pair?
Sorry.
Yeah.
So this one.
What will be this?
Sorry, it will be a list of 1 1.
It won't be a list of 1 1. It will be a list which contains a list 1 and then 1. Okay. It will be a list which contains one and then another one. So how do we, how do we understand this? So first of all, we have this data structure called pair. So pair has this constructor called cons. So whenever I say cons xy, it will create me x dot y. And when I say char x dot y, I'll get x. And whenever I say cadre x dot y, I'll get y. Okay. This is what this data structure is. Yeah. Okay. Now that we are free. Okay. All right. And lists are special kinds of pairs. Okay. What do we mean by special kind of pairs? Lists are pairs of the form element comma list. Yeah. And we have there is a
Sir, can you start recording?
Pardon?
Start recording, please.
Yeah, I started recording. Why? What happened?
So I think you have not started recording.
Start. No. I have started. It's no. It is live streaming in YouTube. Okay. There is a primitive list called nil. Called nil. Okay. Or it's also this empty list. Empty list. Okay. It is also called nil. So therefore, now how do we, given these three statements, lists are special kind of pairs. Lists are pairs of the form element comma list. There is a primitive list called element empty list nil. Now we can actually construct. So if I say cons x comma nil, it will be the list x. If I say cons of, so let's look at what about this one. Okay. If I have this, I know that by my definition, cons of 1 comma nil is the list 1. And cons of 1 comma nil is again the list 1. And cons of this element and this list is nothing but this list. Yeah. So that's how we got that it is the list which contains the list 1 and then 1. Similarly, if I want to look at this one, I know that cons of 1 comma nil is a list which contains 1, and cons of 1.2 is a pair which contains 1.2, because it's not a list. 2 is not a list. If 2 was a list, then it would have been a list 1 2. Yeah. So it's now cons of something, some element comma a list will be 1.2 1. So that's how we got 1.2 1. Okay. All right, and the first one is very simple. Cons of 1.2 is the pair 1.2. Cons of 1.2 is the pair 1.2. And cons of two elements will be cons of 1.2 dot con 1.2. Okay. All right. So that was that is the list listing. Okay. Now let's come back to our last slide. I'll just copy it in here. Do you have any doubts in this so far? Any doubts?
Hello, sir. Sir,
Yeah.
in the good programming practices lecture,
Yeah.
so there is a example where they have used let uh, keyword.
Yeah. Let. Yeah.
So how that is working?
What is let?
Yes. Sir.
Okay. So the so if I have, so what is the let expression? So let expression is of this form: let variable bindings expression. Okay. So for instance, if I have let and then a list of variable bindings. So how should it start? It should start by open parenthesis. Then if I want to say x1, that will be x is mapped to 1, y is mapped to 10, z is mapped to so let's write it one after another. Y maps to 2, z maps to 3. Okay, that is the variable bindings are over. And now an expression. So let's write an expression like plus x plus y plus x y z. Okay. And when I do that, I'll get 6. Now, what is the meaning of that 6? Means that I'm evaluating the expression in an environment where I'm defining y, x, y, and z to be 1, 2, 3. Okay. Now, what is this thing useful for? This thing is useful when we want to simplify the final expression. Imagine I'm writing an expression in which the final expression. So for instance, if x is something like, char of cadar, char of some, let's imagine the expression is like x plus y, some expression like this. Okay. Okay, imagine this is my expression. Now, how does let help me simplify this? So imagine within a function, I have to write this expression. If I don't have let, then instead of this x, I'll have to repeat this expression for 3 times here. Once here, once here, and once here. And that's just blots my expression. Yeah. This is a usual scenario which happens when you are writing functions. For instance, when we wrote quicksort, we had to take care of a list and color of a list and filter and all these things. Yeah. In which case, what I can do is that I can actually use small variable bindings, and then here I could define x to be this expression, y to be some other expression, z to be some other expression, and then one final expression which is rather simple. So in which case my final expression looks simpler, and also it is easy for me to parse. Is that clear what I'm saying?
Yes, sir.
Yeah. Now, what is this a let actually? Anybody? In the first chapter, we actually saw what was let. Let can be basically built using lambda expressions. How?
So using define,
Pardon?
define x, the value.
Yeah. But imagine I have this. I could actually write it using a lambda expression. Yeah. I could say this is actually equivalent to lambda x, y, and z. Now, what is this? This is a function. Now, what is this? This is a function application.
So in the first x1, you have used two parentheses.
Ah. Yeah. So any let expression of this form, I can actually convert it to write it using a lambda. What can I do? I can say that, see, I can define a function which takes these let variables as arguments x, y, z, and then it returns this expression. And to these arguments, I can give these things as to these variables, I can give these as the arguments. Yeah. So actually let is nothing but a syntactic sugar. What does that mean, syntactic sugar? What does syntactic sugar mean?
So easy way of writing.
It is an easy way of writing, but more than that, what it doesn't add any extra expressivity. Okay, so imagine I have a language which only contains lambda. Now I can actually add let expressions. By adding let expressions to my language, I'm not adding anything extra which can be done using the language, because whatever I could do previously, I mean, whatever I could do now, I could do previously also, but by translating the let expression to lambda expressions. So I'm not adding any extra additional expressivity. I'm only adding an easiness of writing expressions. That's what is meant by syntactic sugar. Okay. All right. Any other questions? Questions? Let's try to do an example. Let's try to do an exercise. These are all based on some previous exercises. What could done like this? What would the interpreter print in response to evaluating each one of the following sub-expressions? Did we do memq? I don't think we did memq. of man. All right. Where is it coming from? I have no idea. Can you see somebody writing on my screen?
No, sir.
Okay, let's try to do this one. Define a procedure unique pairs that given an integer n generates the sequence of pairs ij with I one smaller less than or equal to j less than I less than n. Use unique pairs to simplify the definition of primes sum pairs given above. Let's not do that. Let's only do the first one. Define a procedure unique pairs given in integer n generates a sequence of pairs ij with 1 less than or equal to j less than I less than n. Yeah. So what are we asked to do? Unique pairs. So when I say unique pairs of 10, what should I get as answer? I should get 1, 1, 1, 2, 1, 3, etc. 1, 10, then 2, 3, 2, 4, etc. 2, 10, and so on up to 9, 10. Yeah, this is what I should get. Unique pairs. Yeah. All right. Can you do that? How many of you have machine at the moment? Hello. How many of you? Please do it now. I'm going to ask somebody. Sakar. Sakar.
Oh, yes, sir. I will try first on the machine.
Yeah. So what is your strategy? Anybody can tell me the strategy? We should do it using higher order functions. Okay. Any idea? Any idea?
I have an idea.
Yeah.
So what we can do is like we can make another function iter,
Mm-hmm.
which will have an argument as the initial value
Mm-hmm.
and the final value. So the
Mm-hmm.
final value will always be the largest value that is there. And then in the initial value, what we will do is key. Sorry, we will have three arguments: initial value, final value, and now.
Mm-hmm.
The now will contain the number which we are having as the j, which is greater than initial
Yeah.
value.
Let me stop you there. See, the point, you are already trying to solve the problem. Yeah.
Yes, sir.
You are already trying to generate the pairs. That's not how we should go. When we are thinking about in higher order terms, we should think about how can we break this problem into smaller pieces and join them together. Okay.
Okay. Hmm.
So for instance, if I could generate all the pairs 1 1 1 2 1 3, all the pairs up to 10 10, from 1 1 to 10 10, the entire grid, then how can I get the unique pairs? If I have a list which contains all the pairs,
Filter.
I can use a
Filter,
filter.
Hmm.
Yeah. So therefore, I can first generate the entire grid and then filter and get it to this unique pairs. So now I have already simplified my problem, because filter I know how to do, because it's just very easy. All I have to check is that the first coordinate is strictly smaller than the second coordinate. Yeah, that's just a lambda expression and a filter. And generating, once I have the entire grid, then I can filter and get it. I'm not losing any efficiency here, because anyway, this unique pairs is of n square. The entire grid is also n square. So I'm not losing much in terms of efficiency. Okay. All right. Now, if I can generate the entire, if I want to generate the entire grid, how can I further make it modular? Hello.
So you can fix one of the members and then generate that for all. So you generate row wise and then you just concatenate or append all the rows.
Pardon me.
So you can also have a function that takes in one constant and one variable, one limit range, and then it generates all the pairs, keeping that constant and changing that the other till the limit. And then you just have to append all these for different kinds of the constant.
Okay. Not no, not very clear to me. What do you mean?
So just like a for inside a for, but the inner for is a function. So in this case, if I have to generate a grid, I make the inner for a function.
Yeah, but what I want is that I want to write a new extra. I want to minimize the new functions. Okay. I know what is map. I know what is filter. I know what is fold, etc. My simple point is that I want to see the entire whatever I want to do in terms of these things. I don't want to, because it's, see, the point is that why do we want to do that way? Because I mean, you might have your own program, your own logic when you write a function, and that logic is very difficult to convey, especially reading from, understanding that logic from the code is very difficult. But on the other hand, when you say filter, I know what is filter. And when you say map, I know what is map. When you say fold, I know what is fold. So whenever you say you do the fold of this one with this map and then do the filter, it's much easier for me to understand. Yeah. So that's why we want to program in idioms. That's the word we used. Yeah, idioms. We want to have idiomatic programming in the sense that just like when you say in English language, whenever you want to express an idea, you use some standard idioms instead of writing and trying to express the words in your own ideas. You look for idioms which will summarize the idea for you. Yeah, so we want to have idioms in our program. Yeah, so let's think a little more. And by the way, before we go into the problem, there is something which I want you to do. One is it's called zip, the zip function. Okay, zip function. What is zip? Anybody know what is zip? So if I have zip of, let's say, two lists, 1, 2, 3, 4, and 10, 11, 30, 12, 13, 14. What will be the zip of these two things? Anybody tell me? Alright?
List of
Yeah.
pairs of like 110, 211,
211,
312,
312,
413.
or 13. And even though there is one more element in the second list, we ignore that because the first list is complete. Yeah.
Yes.
So zip of two lists, list 1, list 2 will be char of list 1. So it will be, let's call it A1. A1 to AN, B1 to BM will be the list which contains A1, B1, etc. A, L, B, L, where L is min of M, N. Yeah, this is what is zip. All right, let's first write the function for zip. Can you write the code for zip? Write the code for zip. Zip is another idiom. Okay, so like your map filter fold, zip is another idiom. Write the code for zip. Sakar?
Yes, sir, trying.
Okay. Anybody finished?
Yes, sir.
Okay, let's see your, yeah, but why, wait a minute. Anybody is still trying?
Yes, sir.
All right. Okay. You want some more time?
Yes, sir. 2-3 minutes.
All right.
Finish, sir.
Finished? Okay, 1 second. Let's just 2 minutes. Yeah. Okay, let's go. Who was the second one who said he has done? Who was it? After Saina, somebody said he has done. Hello.
It was me.
Yeah. Let's show me your screen.
Okay, sir.
1 second.
Sir,
1 second. Yeah, show me your screen.
sir, there's a small error. I will show you that.
Yeah.
Sir, I cannot screen share. Sir, your screen is still visible.
Sorry. Yeah, go.
So can you see?
Yes.
It's 11
Sip
o'clock.
list 1, list 2. If or null list 1, null list 2, nil.
So I've
Okay,
previously
yeah,
I
that's
have
very good.
given like this. Previously I have given like this. So
Yeah.
when I run that, when I run this list,
Yeah.
it was given like this list like that. So I think I have to make a small change here.
Yeah. One second. Let's look at what you're doing. Okay. So the first line is okay. Second line is okay. Third line is okay. Fourth line, list of
Yes, sir.
list
There is a
of car
problem.
list 2. Okay. But instead of list, what you want is a cons because you want to make it a pair.
Okay, sir. Okay.
No.
Okay, second one, right?
No. You can make it a cons. That one a cons because you want to append. Yeah, that's a cons because yeah. Now combine.
Yes, sir.
Yeah. So basically what you're doing is that you are returning a list which contains you can even replace that list by the first list by cons because
This
then
one.
you will have pairs. Yeah. Then 1.2. Yeah. 2.3, 3.4, 4.5. Yeah, you'll get a pairs. If you want list there, you can put
List here, right?
yeah, list there. Okay, very good. So that was simple. Everybody understood this? Okay. Now let me ask you a question. So I want to check. So this is an application of zip. Check if a sorted list has duplicates. How can I use zip to check if a sorted list has duplicates?
So share your screen, right?
Yeah. So if I have, let's imagine I have a list 1, 1, 1, 2, 3, 4. Okay. This is the list L. LS is this list. What will happen if I zip list ls and cadre of ls? What will be this?
I'll get pairs, adjacent.
Yeah, you'll get adjacent pair. So in this case, it will be
1, 2,
1, 2,
2, 3,
2, 3,
3, 4.
3, 4. Yeah, you'll get these 4 pairs. So you basically what you're doing is that you're zipping a list and the cadre of the list. Cadre of the list is, so it's like placing the list but on top of the other, but shifting it by one place. Yeah. So you get adjacent list. So now once I have this, how do I check if a list has, how can I use this idea, this idiom to check if a sorted list has duplicates? Anybody?
Yeah, you can.
Yeah, sign a stop, somebody else. I know you that but let somebody else come up with the idea. Think. Hello. Siddharth? Siddharth Shah? Siddharth Shah is not here. Who is here? Somebody has to come. Somebody already cut. Devansh? Devansh is not there. Nidish?
Thinking, sir.
Nidish?
Thinking, sir.
Thinking, okay. So everybody understood so far that what is zip of LS, zip of a list and color of the list gives you adjacent pairs. Yeah. Now, if I have a list like this, let's imagine I have a sorted list which has duplicates. Then it will be like this: 1, 2, 2, 3. Yeah. It will be, if I have some sorted list like X equal to 1, 2, 2, 3, and if I take its zip, order of X's, it will be the pairs 1, 2, then 2, 2, then 2, 3. Yeah, that will be my list.
Sir, I have used other than zip, which shows duplicates present.
Yeah, how did you do that?
Sir, basically means I compare the char of list and color of list, and if both are equal, then show duplicate. Else, you can traverse the list till you get duplicates.
Basically, you just search through the entire tree by checking the adjacent elements. Yeah.
Yes, right.
Yeah, that I understand. But the point is that see, the purpose of this exercise is to understand what is idiomatic thinking. Okay.
Okay.
What is idiomatic thinking is not to think of a new novel solution, but use the standard ideas to arrive at a solution.
Okay.
Okay. Okay, so if I do this one, I'll get this. Now, is there a way I could actually get from this to true, false, true? What does this mean? What is this map? What is this function? What is this function I have just applied?
So filter.
No, it's not a filter. I'm applying a map. I'm applying a map, which
So
actually,
if the pair is strictly less than, then it's true.
Yeah. So basically what I'm applying is I'm applying a map, which is lambda pair lambda p then what am I checking? I'm checking if the first and second elements of p are the same. Yeah. So I'm applying this function to Are you getting what I'm saying? What happened? Is this line clear to everybody? What is this this map does? Hello?
Yes, sir.
So basically what I'm doing is that I'm getting these adjacent pairs and I'm applying a map function. What is that map function? It just checks the first and second element are the same. So I'll get true, false, true. So now I have a list of Boolean values and all I have to check is I have to apply a fold function on this. What is that fold? If I have a list of Boolean values, okay, listen to me carefully. If I have a list of Boolean values and I want to take the AND of that, how do I fold? What do I fold? Is the question clear? If I have a list of Boolean values and I want to take the AND, Boolean AND of all the values in that list, I'm saying that that is actually equivalent to taking a fold of the list with some function and some value. What is that function? What is that value? First, we don't have time.
So taking the fold of the list with and the first element would be true.
Exactly. So basically, I take the entire fold of the list with Boolean and the value true. So that will give me the list. That will give me if all the lists are true. So therefore, now checking a sorted list, if a sorted list has duplicates, I can break it down to three parts. One is I take a zip of the list with itself. So that will give me adjacent pairs. Now I apply a map function which takes each pair and check if it is the same. Okay. That will give me a list of Boolean values. Now finally I'll take a fold. And when I take finally a fold, I'll get what I want. Okay, now, so I have broke down the problem into three parts. What did I gain? I gained basically, if somebody understands what is a lot of our problems can be broken down in this fashion into using steps and this and so on, so that when we think in idiomatic way, all this, I mean, even though it might appear that I'm doing something extra, basically why can't I just go through the list and check adjacent pairs? It is fine, but the point is that yeah, I mean, this is more of a, I mean, in this case what happens is that this is more of a illustrative example that one can actually do that way. Second thing is that yeah, it's more of an illustrative example. I mean, because in this case what happens is that the original version is rather simple. You can just go through the list, but while you're going through the list abstractly, you are doing all these three things. That is important. Abstractly, these three operations are happening. It's just that when we do the operations, it's not explicit. Okay, so this is what we call idiomatic programming using higher order functions. Okay, so now for we have only 1 minute left. Can you do exercise 240, 2.40, 2.41, and 2.42? Okay, using the techniques which we learned. So let me. Homework. 2.40, 2.41, 2.4. Okay. And when can we have our this one, our quiz this week? Hello. Hello. When can we have the quiz this week? Siddharth? Hello?
Yes, sir.
Sometime during Friday. Okay? And if
Okay,
you
sir.
you have free time now on Friday?
Yes, sir. We have one class.
Okay. Yeah, so for MTechs, Sakar,
So Saturday.
Saturday.
Yes.
Is Saturday fine for everybody? So Siddharth, just let me
Yes,
know.
sir. On Saturday also we only have one lecture.
Okay, then let's have it on Saturday. Saturday, what time? Saturday, what time?
Sir, our lecture is from 11:30 to 12:30. So any time apart from that would be fine, I guess.
What about 3 o'clock in the afternoon? 3 o'clock.
Fine, sir.
Okay, sir.
All right. Saturday, 3 o'clock. Okay then. Bye.